nice to see you all here, and it's nice to see also because we have Felipe known to most of you here. So let me introduce Felipe. I remind you that this talk is video audio recorded, so you can watch it later. So Felipe Andrade-Santos completed his PhD in 2012 at the University of São Paulo in Brazil, working on mergers in galaxy clusters. Right after he moved to the CfA, where until 2018 he was postdoctoral researcher. Then he moved to Dexter Southfield, where he focused on teaching and was also director of the Clay Center Observatory up to 2012. Today, Felipe is an associate professor of physics and astronomy at the Berklee College of Music. Remains an associate researcher at the CfA, as he has been since 2018. He recently returned to be director of the Clay Center Observatory. Felipe research, as you all know, focuses on galaxy clusters with more than 80 reference publications in the field. And today he's talking to us about using Chandra to re-derive Planck cluster masses and cosmological parameters. And with that, the floor is yours.
Thank you. So it is always a pleasure to be here.
Go ahead, Felipe, sorry.
So
yeah.
Next year, I was thinking about that. Next year is going to be 20 years that I first arrived here at CfA to work with Christine, Bill, and Brown. So, and it's hard to believe that, like, time flies. Like, it's incredible how fast it goes. And despite of that, like being here, like on a regular basis, it's always like great to be here. Always an honor to be here and talk to you. So thank you for having me. So today I'll be talking about how we use Chandra to re-derive masses of galaxy clusters that were observed by the Planck mission, and how we also re-derive it like cosmological parameters using the new masses that were re-extracted. So, as was said, I'm Associate Professor of Physics and Astronomy at Berklee College of Music. They do have a liberal arts and sciences department, which was a surprise to me when I learned about that, and a very exciting moment for me too. I'm the observatory and docent program at Dexter Southfield, a private school in Brookline, the place that I used to work, and now I returned to be the director of the observatory again, and of course a research associate here at CfA. So let me just show you first some images of Berklee students. So the first one there is me giving a talk to the liberal arts and science department faculty on galaxy clusters, lensing, and how we use clusters to actually search for the farthest objects in the universe. And then some students here at CfA. Here we have Bill and Christine. They had just talked to the students. They gave them posters, and you can see the posters that I brought the next day. And so the Bundes cluster poster there in the classroom. And here is the Clay Center Observatory at Dexter Southfield, private school in Brookline. So that's the observatory, the image of the moon. So it's a very nice telescope, especially when you think it's in the school. So it's a 25-inch telescope in the school donated by the Clay family. All right, so I'll start with these slide that took me more than a day to actually make. So we're going to go through a brief and of course vastly incomplete history of models and discoveries leading to what we know about cosmology, and of course that are very particular, very relevant to this talk. So let's start there with Aristotle and Ptolemy. Well, they had a model in which the Earth was the center of the universe. Then Aristarchus of Samos proposed that the sun was in the center of the universe. But there was a problem that the Aristotelian school tried to keep their view of this, the Earth being the center of the universe. They said, like, there is no parallax observed. That was true, and that was a brilliant argument. If the sun was in the center of the universe, there should be parallax of stars being observed. But little did they know that the stars are extremely far away, so parallax was only observed in 1838 by Bessel, and the parallax measurement was of 0.3 arcseconds. Now, I have to make like a little bracket here, and also add the work of like Copernicus, Bra, Sophia Bra, Tycho's Bra sister, and Tycho Bra, and Kepler, Galilei, and Newton. Like they did like major work on our understanding of gravity and how the universe works. Then in 1908, Henrietta Leavitt here from Harvard measured the period luminosity relationship. Seminal and super important work. She looked at that galaxies. She looked at that Cephate stars in the small Magellan cloud, measured the period of pulsation of those stars, and compared to the luminosity of the stars. Actually, the apparent brightness, but they were all at the same distance, basically. So that was just like a factor of like to get the luminosity. So there was this relationship that was determined, major contribution to astronomy that was later used by Hubble and Lemaitre. But meanwhile, Albert Einstein developed his general theory of relativity. And in 1917, Vestus Lippert was the first one to actually measure that galaxies are moving away from us. Out of 25 galaxies, only 3 were not like moving away from us. But he didn't know that the universe was expanding and didn't think about the universe as expanding. He tried to actually explain that by the movement of our own galaxy. Later, Friedman worked on Albert Einstein's like equations and found a solution for an expanding universe. Then Hubble and Lemaitre did their own work also on the velocity, the precession velocity of galaxies, to understand that the universe was expanding. Now, fast forward to 1948, Gamow predicts the CMB, and then in 1965, Penzias and Wilson measured the CMB for the first time, detect the CMB for the first time. Then in 72, Sunyaev and Zeldoch predict the Sunyaev-Zeldoch effect, in which the CMB light is inverse Compton scattered by the hot electrons in the ICM of galaxy clusters. Now, in 1980, Vera Rubin measures the rotation curves of galaxies, of stars in galaxies, and she finds like a pretty strong evidence for dark matter. Now, 1984, Christine and Bill, and there we have like Julia and Daniel in the photo also on the roof of the observatory here. So they did like seminal work on the X-ray emission from a cluster of galaxies using the Einstein telescope. They pioneered like our understanding of how X-ray emission from clusters of galaxies is totally related to the structure and morphology of clusters, and how that is related to the dynamical state of galaxy clusters. Then in 1992, the Cove telescope was launched. We measured the CMB in the entire sky. Then in 1998, 1999, Saul Perlmutter, Brian Schmidt, and Adam Hees They measure the accelerated expansion of the universe. They won the Nobel Prize for that in 2011. In 2020, in the year 2000, the Boomerang mission measured the flatness of the universe, therefore confirming the need for dark energy. In 2003, we have the WMAP with better resolution. And then 2009, we have Alexei doing his cosmology project using Chandra data, which is like really to the top of this talk, doing cosmology with galaxy clusters. And that was like the, at the time, and still is like the epitome of like how you use galaxy clusters to do cluster cosmology. And then in 2013, we had the Planck mission launched, and we were able to use now not only data from the Planck mission to understand the CMB fluctuations and measure cosmological parameters directly from that, but also use galaxy clusters that were detected by the Planck mission to do cosmology in a similar way that Alexei did. So using the cluster mass function. All right, so let's now talk about the cosmic microwave background. We all know what that is. So it's the afterglow of the Big Bang. So this is the Planck map of the CMB, and this is the code, the first feed of like a black body spectrum to the spectrum of the CMB, which fits like a very good temperature of 2.726 Kelvin, and shows how smooth the data is like compared to the model, the predictions of the models. Now, using the CMB, we can actually predict the effect of what happens with light going through a galaxy cluster. So you have the light being emitted from redshift of 1000, that's the CMB light that is permeating the universe. As it travels through a galaxy cluster, about 1 in 100 photons will interact with electrons. So 1 out of 100 will interact with an electron as it travels through the cluster. And when they interact, they gain basically 1% in energy. So the combination of both effects give like a 10 to the negative 4 boost in energy of the CMB, which is about 10 times larger than the typical CMB temperature fluctuations, which is great because then we have this method to actually detect galaxy clusters. Now, how do you do it in practice? Like you measure, with Planck, for instance, you measure the CMB at a certain location, and here you're looking at the same location in the sky, but with different bands. So at the 44 gigahertz, you should expect a decrease. So let me go back here. So what happens is that because of the increasing in total energy of the CMB, the spectrum will be shifted towards like higher frequencies. So there will be a decrement in the CMB where you have a galaxy clusters below 217 gigahertz, and there will be an increment in brightness on the CMB above 217 gigahertz. So if you look for regions where you have that decrement and increment, that's how you find galaxy clusters. That's what we see here. So below 217, which is there on the top, right, we have a decrement. And above there, we have nothing, and here we have an increment. So so when we find increments above 217 gigahertz and decrements below 217 gigahertz, we know that we're looking at a galaxy cluster, the Sunyaev-Zeldovich effect, manifested in the CMB. Now, doing that, the Planck collaboration released in 2011 the first catalog of galaxy clusters that were detected. Well, their first catalog of galaxy clusters that were detected. And in this early soon after catalog, they had 189 galaxy clusters detected. All right, so now that we have the galaxy clusters detected, one possibility is to actually follow up with Chandra to measure the masses of those galaxy clusters. And that's what Bill and Christine led this project. So an XBP project to actually follow up the Planck detected clusters. So Christine Jones is PI of this Chandra Planck legacy program for massive cluster of galaxies. You might be wondering why I have these two drawings there. So on the left, what you have is X-ray emission, so very short wavelength. And what you have here is the inverse Compton scattering of a CMB photon gaining energy after being inverse Compton scattered by an electron in the ICM of galaxy clusters. So here we have those 165 galaxy clusters that are actually below redshift of 0.35. So the Planck mission detected 189, but we had a redshift cut of 0.35 that gave us like a sample of 165 clusters. Two of them were spurious detections. So in the end, we get 163 clusters below redshift 0.35. So previous to Christine's observation of those clusters, we had Chandra observations of the clusters that are in this map here represented by the red dots. So the new XBP Chandra observations added those blue points to the data. So now we have a much better sample and we're closer to being complete in that redshift rate. That later is going to be crucial to do like cosmology. So now that we have the clusters, like what should be one of the main goals of this project was to determine the masses of those galaxy clusters. So how do we determine masses of galaxy clusters? Well, one way of doing that is by assuming hydrostatic equilibrium. So here's all of the math on how you get to the mass, the total mass. But it depends basically on the temperature at a certain radius. So the enclosed mass at a radius r depends on the temperature at a particular radius r, but also depends on the slope of the density and the temperature at that particular radius. So that's how you actually get the total mass within a certain aperture, assuming hydrostatic equilibrium. So here's work from Alexei from 2006, where he measured the masses of like several galaxy clusters. Those clusters were close to being in equilibrium. They were close to being relaxed clusters. So applying this equation makes total sense, and he measured the masses of those galaxy clusters. So here we have the temperature profile of those galaxy clusters we have the data points, like this is Chandra data. We have the blue line here that represents the best fit to the data points, meaning the projected temperature. And the red lines represent the actual 3D temperature, the projected temperature of those galaxy clusters. And the red line here is the one that actually goes into that equation. And then when you get the masses, you can get the total mass of the gas, but you can also get the total mass of the cluster. So that's what we have here. Going up here in blue is the total mass of the gas mass of the cluster. Going down here is the gas density profile. Going up is the total mass, and going down is the density profile of the cluster, the total mass density profile of the cluster. Now, not all clusters are relaxed. We know that. So here's work from 2017 that I did with Bill, Christine, Alexei, and others, Larry. So we actually measured the fraction of cool core clusters in two samples, one X-ray sample and one SZ sample. So clusters that were selected by the SZ effect. So we had 163 clusters in that sample. And then we had Alexei's X-ray flux limited sample. So that was the other sample. So we had 100 clusters in the X-ray flux, or almost 90 clusters in that sample. And we have 163 clusters in the other sample. So Planck detected SZ selected sample, an X-ray sample, flux limited sample. So when we compare the fraction of cool core clusters in those two samples, they're different. So we have more cool core clusters when we have an X-ray selected sample. So that was the main result from that. And then we applied a model that Alexei developed years before to explain why we get more, a larger fraction of cool core clusters. And we could explain the difference between the expected number, sorry, not the difference. We could explain why we get more X-ray, in the X-ray sample, we get more cool core clusters. So it basically goes down to the fact that for a particular mass, a relaxed cluster, will have a higher luminosity, X-ray luminosity, and will be included in the sample when you are flux limit, when you have a flux limited sample. So you end up selecting more cool core clusters because of your criteria. Now, this is just to illustrate the difference between the two samples. On the left here, we have the luminosity of the clusters in the X-ray flux limited sample. And the line that you see there is exactly the expected threshold in luminosity for a flux limited sample. So this is luminosity as a function of the redshift. And on the right, you have the Planck clusters. So the Planck clusters, of course, are not flux limited clusters. So they are spread all over. They do not have to be above that line. And then here is work from 2012 that I did in Brazil during my PhD thesis, that I showed that clusters that are relaxed with low substructure level, they tend to have larger luminosities for a given mass. So here is mass, and this is luminosity. This is the low substructure level sample of clusters that I had in my thesis, and this is the high substructure level. So in blue, you have the relaxed ones, and the relaxed ones develop the cool cores, and they are brighter for a specific mass. So we know that, so the takeaway message here is that we know that clusters are not relaxed entities, and we need to actually treat them as so when we're measuring the masses of galaxy clusters. So how do we do this? So there's an analog of the Y quantum parameter for the SZ effect, which is the YX parameter that was developed by Kravetsov and Alexei years ago. And it's basically like the analog. It's the product of the mass of the gas mass of the cluster by the temperature. So the Y quantum parameter depends on the pressure. And this is somewhat the equivalent of that, but for X-rays. And it turns out it is extremely robust way of measuring masses of galaxy clusters. So all of the calibrations, all of those results were presented in Kravetsov 2006. So that's how we're going to measure the masses now. We're going to use the gas mass of galaxy clusters and the temperature. And then the multiplication will give us the YX parameter. And from that, we can use a scaling relation to get actually the mass of the galaxy cluster. So the scaling relation that was actually calibrated for the cosmological project, Chandra cosmological project of Alexei. So it's given here in this equation. So what you get now is that if you measure the y-axis, you can get the mass. It's being calibrated. And the Planck mission does something similar. You get the YSZ effect, and you get the mass out of that YSZ parameter. So, and on top we have Alexei's equation for the density profile of galaxy clusters. It's a modification of the beta model, where there are terms that include that are included to better fit the density profiles close to the core and close and this low at the Callard radii. So that's a more it's more complex, but it's a better equation to actually describe the density profile of galaxy clusters. So when you do that, so you get the density, you get the mass of the gas mass, then you measure the temperature. Once you get the y-axis parameter, you insert in this equation and you get, like, because of this scaling relation, you get the total mass of the cluster. So the y-axis parameter gives us the total mass of the cluster. Now, the Planck collaboration, as I said, does something similar. They do actually get the YSZ, which is the equivalent of the y-axis, to actually measure the mass of galaxy clusters. But to do that, they had to calibrate that method too. So they used a sample of XMN Newton cluster, observed clusters, and they measured that for 47 clusters. So they measured, assuming hydrostatic equilibrium, they did some lensing analysis, and they had the masses of a group of, or a sample of 47 galaxy clusters. And with that sample, they were able to calibrate the method. They have the YSZ parameter for all of the clusters, but they don't have the masses for all of the clusters. So the idea is that you have the YSZ, and now you need to calibrate that against the mass, or the mass against the YSZ. So here is what we did in 2021. So we had a sample of 147 galaxy clusters that were detected by the Planck mission. So out of those 163 galaxy clusters, part of Christine's XBP project, 147 were not bimodal clusters, and we could measure the masses very well. So we had this sample of 147 galaxy clusters. They are not flux limited sample. They are not part of the flux limited sample. Now, for comparison, we also had 80 clusters from the flux limited sample that I talked about before. So what we did here is that we re-extracted the masses of those clusters. So we re-extracted masses using the y-axis parameter that was calibrated. So we measured the y-axis, got a mass. So we re-extract the masses of all of those clusters, and we compare to the masses that were given by the Planck mission. And here you look on the left, like you can see that there is very good agreement between the masses determined by the Planck mission using the YSZ parameter. And so here is the here is the YSZ and here's the y-axis. So there's a good agreement between those. Now, when you express that, not in intrinsic properties, but operant flux in units of arc minutes, square arc minutes, you can see that the slope changes. It's the same sample, just expressed now in terms of operant flux instead of intrinsic properties. And the slope changes. Well, I'm going to go back to that in a minute, but that was like a puzzle when we saw that. Like, why simply changing from one to the other? We didn't do any new calculations other than simply multiply by some factor that depends on the redshift of the cluster. So that's how you go from that plot to that one, okay? It depends on the angular distance of the cluster that depends on the redshift. So the slope changes. I'll go back to that in a minute. Before I go back to that, from the y-axis parameter that we can measure using Chandra data, we can measure the mass of the clusters. And from the y-z parameter, they can measure the mass of the cluster also. So comparing here, the masses of those clusters obtained using the y-axis parameter, using Chandra data, and the y-z parameter using the Planck data, we get a very good agreement between the two. But then what we did, we used the new centers of the galaxy clusters that were determined from the Chandra data. So the Chandra data with an angular resolution of the order of arc seconds can pinpoint where the center of the cluster is much better than the Planck mission with a resolution of the order of arc minutes. So with a new center for the clusters and a new radius, R500 for the cluster, we re-extracted the masses of the clusters using the SZ technique. So we used a MMF, which is the multi-match frequency algorithm to actually go to the Planck data, re-extract the data, now using the new center and aperture that we got from Chandra. Therefore, like here is a very good point about how complementary Chandra is to this, because Chandra was able to determine with much better accuracy where the center of the cluster is. Like we have a very good angular resolution with Chandra. And then we were able to re-extract the masses that the Planck mission derived. When we did that, we got pretty much the same slope, but as lower scatter. Okay, so we decreased, and we were able to decrease the scatter by a little bit, but not a bit, by 50%. We were able to decrease the scatter in the slope in the relationship. The slope was the same after re-extracting the masses. Then we published that. Now let me go back quickly to the fact that we see different slopes here. So that's YSZ and YX parameters. And this is YSZ and YX parameters, but in different units. Here in operant flux, here in intrinsic properties. And how you go from one to the other is basically by multiplying by a factor that depends on the redshift. When you do that, the slope changes. So I did some work, some analytical work. I'm not going to go over all the calculations, but it turns out it's a mathematical property. It has nothing to do with physics. It's just a mathematical property. So what happens is that when you reorder the data, the slope will get closer to 1 and the spread will increase. Okay, it's a mathematical property. I'm not going to go over the details here. If you have questions, we can talk about that later. But I was able to show that analytically. Monique Arnaud, by the way, asked me to do that analytically because I had shown, like, with a simple, like, model, a computer code that I did, like, that it was changing. And she asked me, can you show that analytically? And at the time, by the way, I was working in the school, and one of my duties was to take care of the kids, like and that was during COVID. So I had to take care of the kids, make sure they were wearing the masks. I was in a room there, like I was a proctor of this study hall. And I was there, so I would bring my papers and I would do the calculations. And so from time to time, I had to stop one of the kids, ask them to put the mask back on, like, but that's how I actually did all of those calculations. Okay, so I was there, like, just taking care of the kids, making sure they were not burning the place, and doing some calculations in between. Okay. Now we have the masses. We can do cosmology. Okay, so Well, we all know the formalism for that, the projector formalism. Not gonna go over that. So here is like, by the way, a little work that I did years ago, working with Alexei, trying to simulate what the X-ray background would be for links. And then we use it like some, well, I coded in Python to get like images, like fake images of like or mock images of what links would observe. But anyway, here is a plot that shows sigma 8 and omega n. They are highly degenerate. When you measure, when you do cosmology, they are highly degenerate. And how the mass, how the normalization of the mass plays a role in these measurements here. So if you're wrong in your mass determination, you're gonna be biased high, both in sigma 8 and sigma 8. Therefore, it's really important to measure masses like very well. All right, so Gaspard Emmerich, like a student working with Gabriel Pratt in France and others, he did very nice work on cosmology using the Planck clusters, but the X-ray data that we got from Chandra. So let me just summarize here what was done. I encourage to actually ask him to come here or to give a talk, a remote talk about that specifically. So what happened is, to summarize that, here we have a comparison of what we did in 2021 and what he did in his work in terms of the YSZ parameter. So in 2021, as I said, we had a new center for the galaxy clusters and a new aperture for the galaxy clusters. We went to the Planck data, re-extracted the YSZ parameter doing that in 2021. He did the same thing again using his own algorithms. So this is a comparison of the YSZ that we obtained by re-extracting YSZ directly from the Planck mass data with what he did now. So that's very reassuring that like he was doing the right thing. We got like very close to one relationship between the two independent methods that were used. He developed his own algorithms for doing MMF, and we used the similar algorithm that was used by the Planck mission, so in 2021, and we got like a very good agreement between the results. All right, so now how do you do cosmology? How do you do cosmology with the new masses? Well, as I said before, the Planck mission detected 189 clusters in 2011. There was the ESZ sample, but later they continued to detect more clusters, and they had a sample of 1,653 clusters. And that's the sample that they actually used to do cosmology. So 1,653 clusters. But they only had masses determined using X-ray or XMM Newton for 47 clusters. So what you do is that you calibrate your YSZ parameter that you have for all 1,653 clusters against the mass that you have for 47 clusters. That's what they did. That's what the Planck collaboration did. Now, what Gaspard did is that he used our sample of not 47 clusters, but 147 clusters that were measured, that we had Chandra X-ray data. So he, instead of calibrating the Planck YSZ against the XMM Newton masses, he calibrated now the Planck YSZ against our Chandra data due to like Christine's XVP project. So that's the idea here. So you do cosmology by obtaining the masses of all of those clusters, 1,653 clusters, by actually calibrating or getting those masses from a calibration. So he did that. And then one of the steps that was required to be done was to actually look for or to correct for the bias. So we had the masses. We provided the masses for Gaspar, and he used like a weak lensing masses of 100 clusters, the largest so far to be used for this kind of calibration. So 100 clusters were used to actually correct and estimate the bias effect between the masses that we measure and the YSZ parameter. So once he did that, he gets like a relationship between now the mass and the YSZ from the Planck data, and then he applied the whole he re-derived or he reanalyzed the Planck data all over again, but now with a new calibration. So just to summarize, like we were able to provide the masses, the new masses, for a much larger sample, and he was able to calibrate the YSZ parameter obtained with the Planck mission against our X-ray sample, our Chandra sample that was originally observed because of Christine XVP project. And here is just a summary of like the results. So we got now omega m, sigma 8, and S8, which is the product of sigma 8 by the square root of omega m normalized to 0.3. Okay, so that's the values that we got with Chandra, and that's the values that were obtained before with XMM Newton, meaning the calibration using XMM Newton data. And they are very, very compatible. Okay, another reassuring result here. And with that, I end my talk. I'll just show you why I am at Berklee College of Music. That's why, okay?
Any question? You play instrument?
I do play guitar, yes. And by the way, these are guitar gods. Those are legends of guitar. Like, these are among the greatest guitar players that ever lived. And that was in 2000, funny thing here, that was in 2016, a concert in New Hampshire. The reason I'm there with them is because I paid $400 for the VIP ticket so I could go backstage. And then part of the package was that you get to be in the front row. That was a big mistake. Like I was just in front of the amplifier. Like at some point I had to go to the restroom, get some paper, get it wet, and put inside my ears because I thought I was gonna be dead at the end of the concert. Okay.
Sorry for taking you away from the music.
Yeah, let's go back here.
But a very basic question. You started your talk by explaining how these clusters are detected in Planck data by looking at the increase of the fluctuation versus decrease of the frequency. How likely is it that could happen by chance and not related to a cluster? In other words, how often do you see these fluctuations and they end up not being Chandra detections in clusters?
So I'm gonna answer that with two slides here. So the first one is that effect is much stronger than the typical fluctuations in the CMB. So there's that in general. But yes, there are false detections. Like one example here is right here. So I said that Christine's XVP project to follow up with X-rays the Planck detected clusters and 165 clusters. But it turns out there are actually 163 clusters. There were 2 false detections there, okay, that had to be excluded. So it happens, but it's very, very unlikely because the signal is very, very strong compared to the typical CMB fluctuations. And the Planck data, and that was from the first 11 months of the Planck mission. Later on, after Planck scanned the sky several more times, like the reliability became even higher. Does that respond?
I could comment on that. I mean, South Pole Telescope, we now have about 5,000 SD detections, and the problem with the purity of the sample is if you go look in the sky and the visible and look for a cluster, the reason you don't see a cluster usually is because it's a too high redshift. And so that's true of about 4% of the clusters. And if you really drill down in the infrared, looking for the clusters, you generally find it. I don't actually know of any examples of something that really looks like SD effect and is not a cluster somewhere at some redshift. I have a question for you.
Yes.
So you get an absolute calibration in mass from the X-ray measurement, and you get another absolute measurement of mass from the weak lensing. And how similar are they in your data set?
So we can look at the bias here.
Is that what you mean by bias?
So here's the bias for Chandra and X7 Newton. So Chandra is off by about 10% compared to the equivalency masses.
Yeah, well, that seems like a lot. Is there an explanation of that in terms of physics? I mean, why is your X-ray measurement, which you've convinced us is a real measurement of hydrodynamics of the clusters, why is that off compared to the weak lensing? Maybe the weak lensing isn't accurate enough. I don't know. Well, it's actually only a 2 sigma factor, 2.5 sigma.
Well, it turns out the X-ray is sensitive to the even though we can do like the Y-X parameter, it is more sensitive, or it is sensitive to the dynamical state somehow. Mm-hmm. Now the weak lensing is not. So there's that. Like even though we have like robust methods to actually measure the masses with X-rays, they are not totally like insensitive to the dynamical state.
Isn't there a shape assumption as well?
There's
a shape assumption?
Not really, right, Alexei? Like the shape when it comes to, we had a discussion about the shape of the
Yeah, they are under assumption of spherical symmetry, but this is part of the possible bias. There can be dynamical state, deviations from spherical symmetry, magnetic field pressure, cosmic ray pressure, turbulent pressures, all this stuff is potentially contributes to the bias. Very good. Calibration of Chandra contributes to the bias because temperatures is what we derive from the spectrum, not from.
Any more questions? Okay, well, in this case, let's then Felipe again.